Okay, hello everyone. Thank you for coming. I'm Nikolai Kondrashov. Just waiting for a sound check. Is it working? Okay, I'm Nikolai Kondrashov, and I'm here to present to you how to, very quickly, how to produce a firmware for a microcontroller from scratch without using any libraries. I only got 25 minutes, so I'm going to go very fast. These slides are available on FOSDEM page and also on my Twitter page right now, if you'd like to see them closer. So I do this stuff as my hobby. I have not studied it in university. Actually, I dropped out twice and haven't finished my university. So if I can do it, you can certainly do it. So what we're going to be talking about, I just was playing with BeagleBone Black and trying some assembly stuff. And then I decided to build something and bought an Arduino. And I burned it. And I thought, that's a bit of expensive if I buy it again, original Arduino. So I found these little boards which have this microcontroller on them, and they cost, with the stuff that you need to program, it costs like €3.50 with delivery. So you can start easily. You can buy 10 of them and burn them all and learn from that. So this is the stuff that I was able to build with it. This is out of Lego and scanner and printer parts, and then some EEPROM dumping, and then this little Christmas present for my wife. And this is what I'm working on right now. This is a printer interface for the ZX Spectrum, for the bus of the ZX Spectrum, not the serial one. You will still need one library, and that's your library that you're going to use. And or rather, I should call it documentation stack, because there are layers and layers of it. So the first, of course, is the board documentation. And by the way, have anybody programmed a microcontroller here before? Okay. Anybody? Anything except Arduino? Wow, that's a lot. Why did you come? Okay. So I hope I will be able to tell you something new. So starting with the board documentation, you can find it on the web with this name of the board, and there is a manufacturer's website. There is some stuff. Then there is, of course, the data sheet for the microcontroller on the board, and the microcontroller family reference manual, which is the biggest one here, and this is the one that you will use the most, because it has the description of how everything works, all the peripherals, how they are connected, and what to do with them. Then there's the programmer's manual, which gives you like programming tricks and things. And of course, the technical reference manual for the Cortex-M3, which is the CPU in that microcontroller. And then finally, the architecture reference manual to find out all the things that you need. This is basically all that you need, maybe just a little extra. And then this is a lot of documentation, like 2,500 of pages. But don't be afraid of them. They're very well written, these specific ones, and I expect many microcontrollers have very well written documentation which tell you what to do. So the board from the top is USB socket, boot configuration pins, reset button, MCU, the 8 MHz system clock, crystal 32 kHz real-time clock, and power and user LED, and the serial wire debug header. So if you look at the first page of the data sheet, you could see that its maximum speed is 72 megahertz, which has 1.25 MIPS per megahertz, which is 180 times more than that spectrum that you saw before. And it also has single cycle multiplication and hardware division, which is amazing. It has not that much memory, actually less than the first ZX Spectrum had. But it's enough for the microcontroller, and lots of pins, although this specific chip has not 80 but less, but still most of them are 5-volt tolerant, which is great for experiments and for 5-volt logic. And of course, plenty of peripherals. So how to get your program? So you got to look at the datasheet first, and it says that bootloader is located in system memory, whatever that is, and it is you can reprogram the flash by USART1. It doesn't say anything else, but reference manual says that you can affect which memory is mapped and which memory is used for booting using the boot pins. And then this specific configuration will boot us the system memory, which is where the bootloader is. And if you look at the board documentation, it also repeats this table here, and it says that the ISP, which is an in-circuit system program, I'm sorry. It's basically the same thing as the bootloader in this case. And if you take a look at the default configuration, you need to change just this jumper. Then finally, you need to find out where to actually connect, where the bootloader is listening for USART, and that's visible in the separate document not mentioned before. It's a big document summarizing all the configurations of the bootloaders on all the boards that ST produces from this family. And it says that there's the RX is on PA10 and TX is on PA9. And here's the pinouts basically mapped out for you. And don't forget to cross the serial TX and the RX as usual. And you can supply the power from the serial cable, but I found that it, for some reason, doesn't work very reliably, and sometimes it doesn't turn on. I don't know, maybe the cable is not very good done, or there's the voltage regulation doesn't work very well. So in that case, you can just take a separate mini USB cable, micro USB cable, and connect it. But don't forget to disconnect the VCC. By the way, if you manage to give me any questions, there is a present for the best question is one development kit. So that's how it will look if you connect everything and power it on. Then what to do, how to flash it, you can just basically look for it in your Linux distros, and you will find STM32 Flash, which is exactly the tool that you could use for that. And it has a ton of features, and it works very reliably for me. So while we don't have a program yet, we can already use that tool to verify that everything is connected right and everything works, and find out the board parameters. So you can see that this one is 128 kilobytes of memory, which is normal for all the recent boards like this. Then, before I go into the next section, you have to remember this one thing. So I guess the embedded engineers don't often say this, but it is easy and fun to do this. Well, of course, unless you're paid for it. So there's the initial very steep ramp in knowledge, but once you get past the basics, it's really easy and fun, and if you don't have a deadline, it's very satisfying. So of course we're going to blink the LED, and we'll start by finding where the LED is connected, and this is the manufacturer schematics. This is all of it basically, and there is the LEDs, and the Google Translate says that it says D2 is programmable. So this is the one we need. But it's very curiously connected that its anode is connected to the powers directly, and its cathode is connected to the to PC13, which means that to turn this LED on, we need to pull the pin down, which would be counterproductive. If you write 1, you expect the LED to light up, but we need to do the reverse here, and that's because as the pin description table in the datasheet says, you got there's a little footnote there on this pin description number 5, and it says that this is connected to the power switch, which has only very limited current capacity, 3 milliamperes, which is not enough to drive the LED. So you should not do that to use it as the current source, and you should also limit this speed to 2 megahertz. And must not be used as a current source to drive a LED. And so the board creators were very economical, and they used one of the most useless pins to drive the LED, because it doesn't say that you cannot use it as the current sink. So next, so we are ready to sketch out our program. What we need to do is to configure the PC13 pin for open drain output, 2 megahertz max speed, and we need to do an infinite loop and wait a little bit and then toggle the LED. That's all we need to do. Well, there's a little more, but we'll see just in a moment. So we have our program, but we need to tell the microcontroller to run it somehow. So the vector table comes in, but first, before that, we need to see the ARM CPU reset behavior. And we're not going to go through all of that. There's just a piece at the end here. And it says that the CPU gets the vector table address from the V2R register, well actually some of the highest bits. Then it takes from that vector address the first entry, which is 4 bytes, and puts it into the stack pointer, which is the stack is full descending stack. That means that the stack pointer should point right above the stack area. It always points to the last end, the entry that is pushed last. So our stack pointer should point right above the stack pointer. Then it takes the next 4-byte entry from the vector table and branches to it. That's our reset handler. So what we need to do is we need to somehow allocate the stack. We put this right here. It's not normally done that, but we can do that. There's the vector table. So we put our stack address that is above the stack, and we put our reset handler. But next, we don't know what's the actual vector V2R register at the reset. And we don't know where we should put the vector table. We don't know how. So if we take a look at the architecture reference manual, it says that it is 0 normally, but it can be overridden by implementation. So we check the implementation, and it says, on system reset, the vector table is fixed at address 0, which is great for us. So let's look at what's happening at address 0. It's memory map from the datasheet. And here we see that at address 0, we can have either flash or system memory. Remember that system memory, that's where the bootloader lives. But we can also have flash, and it's dependent on the boot pins from that table. Which means that basically what we need to do is to put our vector table at the start of the flash at address 0. But we also see that flash memory is normally living at 0, 8, and all zeros. So we need to make our code be aware that its location will be there. And furthermore, we can, while we're here, we can check where our SRAM is. That's where we should put our stack and all our global variables. So we can tell that to linker using a linker script. So first we'll define the memory regions in the flash, where it starts, how long it is, and being safe, saying that 64 kilobytes, that's what we certainly get, but usually it's 128. We tell it that it's a read-only executable region, and then we tell that SRAM is read, write, and non-executable, where it starts and how long it is. Then we can start putting in sections. We have the special section vectors that goes to flash first because it has to be at the start. Then we put the code next. Then we put the read-only data, which we don't have yet. And then we have the global variables going into SRAM. So now we still need to tell the compiler to put our vectors table into the vectors section, and we use that using the GCC attributes, and we tell it like put it into vectors section, so it ends up at the start of the flash. Now next, so ARM uses memory mapped I/O, which means that you talk to peripherals by writing to addresses using the same instructions that you would use for accessing memory. And this is the area where all the STM peripherals live, this little piece in address space at this address. And here they are, all of them. There will be several instances of the same peripheral type, and there would be the same. They would have the same register set and the same semantics and everything, just different base addresses. So they don't say it in anywhere in the manual. That's normal, but you actually have to enable your peripherals before you use them, which is not the same for all microcontrollers and CPUs. Like for example, for AVR, as far as I could see, you don't have to enable much to start using peripheral. You just can go at it. But for example, for AM335X and BeagleBone Black, you have to enable power as well as clock. And for this microcontroller, you just have to enable clock. So what you see here is the clock tree. Don't be scared; it's not too bad. And what it says in the manual is that at reset, the microcontroller is running from the internal oscillator. It's called a high-speed internal oscillator, which is basically an NRC oscillator here. It's running at 8 megahertz. So that's how we are able to start executing anything before we have the clock configured. So it doesn't say where our GPIO-C port is connected here on this diagram. So we can dig further at the system architecture, and we can see that GPIO-C is located here, connected via APB2 bus, via HB system bus. So that's where it's probably on the clock diagram. And if you look here, still closer here, it says that it's connected here, and we can try to trace out how the clock gets there. So what we need to do is probably control APP2 bus settings to enable the peripheral. And we didn't actually need to know all that. We can just look at the registers for reset and clock control peripheral and see that there is a register at this address and this bit, and it controls how the clock to that port C. Finally, we need to determine where the peripheral lives, and it's this address here. Now we can actually enable our port. We take the register, the peripheral address at the register address, and then we write the bit 4 there. Our port is enabled. Now we can start configuring it. So I usually read the whole peripheral manual before using it, but we just run through the registers. So there are 2 configuration registers because there are 16 pins, and each requires 4 pins for configuration. So there's configuration register low, configuration register high. Then we have the input register to read the data from the port, the output data register to output data to the port, and then we have the set reset register to atomically set or reset register the pins, and reset register, probably legacy, just for resetting pins. And finally, the lock register, which allows us to lock configuration, to, for example, to avoid damaging hardware if our program goes haywire. There is also a table describing all the possible configurations of the pins, but we just need the general purpose output, open drain. We need to set these bits in these fields in the register for 2 megahertz, and then we can use ODR register to control the output. So on the typical I/O pin diagram, we'll be writing to output data register or reading from it because we're toggling it. We'll be controlling the output by turning on and off this NMOS here, so NMOS transistor. So when we have one, we'll have high impedance on the pin, like nothing is connected. That's what we need for the LED to prevent any damage to the pin. And when it's 0, it connects it to ground, allowing the current to flow and light the LED. So this is the configuration register high because it's pin number 13, so it gets the high register. This is its address, and we need these 2 fields, number 13 mode and 13 configuration, and we need the output mode max speed 2 megahertz, as I said before, and we need the general purpose output open drain configuration, and finally the port peripheral address is here in the memory map. Now we're able to configure our port. We write the register address, and this is a bit of math here for you. It didn't have to be like that. It's just fancy. So finally, we need to control the pin. This is our output data register at this address, and we need the bit 13 to control it, and we can write it down, the register address, and here we are toggling the bit. What's left is just the wait, and we can shortcut here, just do the wait like this. So then we need to build it. So you need the bare metal ARM tool chain. It's available, for example, in Debian. Install it, and then we can ask the compiler to use the Cortex-M3 to build for Cortex-M3 CPU. Just compile, don't link, because it will just use its linker script instead. And then we tell the linker, use our linker script, and output an ELF file. And then, while we're still here, we can take a look at our ELF file and see where everything went. So our vectors table went right to the start of the flash over there, and it's 8 bytes long. Our reset routine went right after that in flash, and our stack is allocated to be at the start of SRAM. So now we can convert that ELF file to a binary, like pure binary, basically what we're going to be flashing. We can take a look at it again and see that the first entry is the end of our stack, and the second entry is our reset handler, and it has bit 1 set to indicate that it's a thumb mode, which is the only mode available for this CPU. And finally, the rest is our reset handler. So to flash it, we use STM32 flash. We tell it flash that binary file and verify whatever you write. And there's our board on USB 0. It takes a very little while because it's very short, and now we're able to run it. But first we need to switch the boot pins back to have the flash mapped at the boot hub so that our program can be there at the 0 and our vector table. So we just put it back in the default position. And that's how it would look. Very exciting. So another takeaway is that all this hardware, people worked hard on it, and they had lots of customers before you and lots of engineers before you, and they tailored it exactly to your default use cases, exactly what you want to try to do when you just start with your hardware. So, and in the end, you will need to tweak just a few bits to start working, to start your peripheral going. So it is going to get you very far. Okay, so obviously you don't want to always copy those register addresses and all the layouts all the time in your program, so you can write a library, and different people do it differently. Some people do it in a very weird way, especially hardware engineers, I'm sorry. But it's up to them, and somebody will see my way as a very weird one. So I just put the register location into structure and store the peripheral addresses, and then I describe all the bits, all the bit locations and everything using macros. And that's probably the most boring part of making things work from scratch, where you have to copy these cryptic register names from the manuals and everything. And it reminds me of how I used to type in the programs from the magazines in the past. So next, the default clock is 8 megahertz, and the maximum is 72 megahertz. If you want to do something fast, you got to change that. I'm not going to explain how to do that, but here is approximately how it would look. You go through the external oscillator, and it's stable, more stable than the RC oscillator. You go through the PLL and tell it to multiply by 9 to get 72 megahertz, and switch to PLL when it's ready, and then you have your 72 megahertz clock. There are a couple gotchas like this one. So if you go very fast with your clock, the flash won't be able to keep up, and then you have to configure flash so it tells the CPU to wait while it fetches the data. Otherwise, the CPU won't be able to read its code and won't be able to execute anything, which has actually happened to me. I was scratching my head, and this was one little thing I was able to find eventually. So, and then, for example, the APB1 bus, it has the maximum speed of 36 megahertz, so you have to set up dividers to lower the clock speed for that bus. This is all the code that it takes to get to 72 megahertz from my library. I'm not going to talk about that. Okay, so if you want more peripherals, remember, the documentation specifies lots of steps that you need to take, exactly the registers you need to modify to get to specific application, like communicating with via USART, with DMA or things like that, and each peripheral has descriptions how to do this application or to that application, and they usually go to great length and more complex case than you need initially, and which means like this has transmitter procedure, then receive it procedure, but it boils down to this if you want to just receive a byte and send a byte. And this is all configuration, like from enabling the clock and everything. That's all you need. I didn't test it, but there is these yellow lines are all links. You can go and take a look at the code and try it yourself. Similarly with the timers and the PWM, for example, very popular application. It describes everything that you need to do, all the registers and everything. And then this is all it takes to blink an LED on a pin using PWM. And ADC, very simple, again, single conversion mode. And the continuous conversion is also not that hard. So that's all the code, including calibration and enabling everything and receiving a value from ADC. SPI, same thing, very well described, transmission, reception, and that's all the code configured. There's a lot of bits there, but you just copy that from the manual. And finally, go and experiment. Okay, any questions? Yeah.
So what kind of tools or techniques that you use in order to debug your programs on this?
Well, you can always toggle a pin or light an LED. That's what I do. I just put a
so I have something to add. There's a cool project called Blackmailing Pro. If you have two of those, you can flash it on one of them and then contact using serial wire debugger. and you have like a full GDB using that thing. So
Yeah,
like Magic
yeah.
Pro.
Yeah, the serial wire debug, of course, you can use, but I don't bother. I just light on LED because my programs are usually not that complicated. Or I use the toggle a pin and watch with the scope and see like what's the timing and things like that. Okay? Yes?
Yeah, can you use the SDM utilities to read the firmware back from the chip?
I think so. Yeah, I think you can read the. It comes by default with something that blinks, so you can read that if you want. Anybody? Yes?
Is there a specific reason for you not using C++ in that thing?
It's very, very,
You could have done context to variable.
yeah, there's very simple reason. I don't like C++. I know it's very useful, but it's just my personal preference. Maybe I'll come around. I started with C++. I was reading Bjorn Stroustrup for the night, you know, like. So, anybody else?
Well, anyway, you don't have space for the STM.
Okay, thank you very much. And debugging question, please come.
Thank you very much.
You're welcome.